So I want to do a little bit of a deep dive, and I'm going to try to bring it back and talk about the general concepts that I'm talking about, because it can get quite technical. But first things first, what is a power spectrum? What are we trying to do here? We're trying to measure the epoch of reionization and its distribution of cosmological structures in Fourier space. And so we use the power spectra because then we can add up in 3 dimensions and get better signal to noise. And so the more power you have in a specific, on a specific scale, shows you how many bubbles of the EOR were of that particular size, roughly. And so theoretically, we expect the EOR to fill most all K modes. And we expect the foregrounds to vary spectrally smoothly. So hypothetically, they should have some sort of power law association with them. But in reality, we see something like this. So the instrument itself is chromatic. The instrument has a frequency response that we can't get away from. And so that actually couples the foregrounds to many other modes. And so within the EOR community, we like to refer to these 2 sides of the plot. You have the EOR wedge towards the left side here. This is contaminated by our instrument and our foregrounds. However, there's still a lovely little EOR window to the right. And so rather than really spend a ton of time on the EOR wedge to measure those particular modes, we generally try to do a foreground avoidance technique. But if we go even further into a realistic scenario, if you introduce errors on the form of roughly 0.1% in the calibration, so that's 0.1% difference as a function of frequency due to how you calibrated, you can actually take that foreground power and bleed it out through all of the modes. So you can no longer measure the EOR anywhere. And so that's something we've been fighting for the past 5 years or so. And so I want to take a step back and have a look at what our interferometer is doing. So this is a very simple diagram of an interferometer. And this is the visibility equation here on the left. You have a beam response, that's A, that's what your antennas see. You have a sky intensity, that's the actual flux from the sky. And you have a geometric phase term. And these are the 3 parts that go into the interferometer equation. And each of these 3 parts is important. So most of the time, you'll probably only see the sky intensity in the geometric phase term because the beam response, it's like 1, right? Like mostly 1. But in fact, it, as I'll show, it has a very significant response. So if we take a look at that A term is what the instrument sees. This is what the instrument sees. So if you were to lie flat on your back and look up from the Murchison, and you pretended you were a radio telescope, this is what you would see. So in the middle, it's 1. That's your primary lobe. And then you have these side lobes. And that's because you don't have a perfect dipole. It's just how it is. And this is discrete. And so what we do is we Fourier transform this, we FFT it to create a beam response in UV space. And we then use that UV response to do convolutions and add things up together quickly. But again, that's discrete. So I have to do an FFT, and I can't do any analytic simulations with something that's very discrete. And so I want to play with this. Instead, I want to decompose this into a series of Gaussians, because a Fourier transform of a Gaussian is a Gaussian, so I can turn this into an analytic form. And this is roughly what that looks like. This is good to within 0.1%-ish, again, 0.1%. So it's a fairly decent representation. But what it will allow us to do is to do instrumental simulations that are not too far off of what we expect the instrument to actually see. And so this isn't necessary, but it does show you that we can now go into basically a wonderful little analytic simulation. And I can turn on certain aspects of the pipeline. And what I'm going to show you today that has significance is if we try to calibrate with this analytic scheme. So you have an input and then you have something that you calibrate to. So if your input was semi-analytic and your experiment was semi-analytic and you used an instrumental kernel, so you actually represented the full sky, you get this beautiful power spectrum. It's not showing up here, but the EOR itself is roughly here. So the EOR level is at roughly 10 to the 0. So as soon as you dip down below here, I don't have the EOR simulation in this simulation. So this shows like the level of errors. So you have this beautiful EOR window. Ta-da! You could measure the EOR here. But if you turn off aspects of that Gaussian decomposition of the beam, because it's a series of Gaussians, I can just flip certain Gaussians off and see what happens. You can start to see significant contamination. And this contamination is very much reminiscent of the errors that I showed at the very beginning as well. So this is indicative. If you were to take a takeaway from all this, is that your beam has to be extremely, extremely accurate. You can't just ignore your side lobes. Even worse, though, is that even if you had a perfect beam, but you discretized it, so instead of having a semi-analytic input and a semi-analytic experiment, you had a discrete experiment, you have significant contamination above the EOR in the EOR window. So even in the best of times, we can't measure the EOR with our current infrastructure and techniques, because we need to use discrete methods in order to average up hundreds of hours of data. We can't necessarily use these analytic formulations. They took forever to run. So that's bad. But there's something even worse. Sorry about it. So if you add a horizon, things change, because this Gaussian decomposition, it's missing that hard edge of the horizon, right? But I can still add that in analytically. So it's a series of Gaussians on the left multiplied by a spherical top hat. So you can do a convolution to make an analytic for a transform of that. And does anyone see immediately what's wrong on the right? It's infinite. It's infinitely extended. So the Gaussians themselves are infinite, right? But this is infinite on levels that matter. So I can't represent this beam well at all, because I have to go out in infinity direction in Fourier space, and I can't. So I have to truncate it at some point, and no matter where I truncate it, it's so high that it causes contamination in this window. And this is roughly at the EOR level. And you can turn off certain aspects again of this Gaussian decomposition. I can do that. And you can see I have 3 different types of beams here on the right, just playing around with like, oh, what if I didn't have side lobes? Or what if the side lobes were lower? And you can see that if you didn't have any side lobes, so the bottom one, there's no interaction with the horizon. There's no hard edge. So there's no longer an infinite extent to the beam kernel. And as a consequence, the power spectrum looks lovely. And so the question here is, what is the beam doing at the horizon really? Is the beam slowly coming off at the horizon, or is there a hard edge? Because you could say like, oh, this is just projection effects, Nichole, like do spherical harmonics, but that's not good enough if there is actually a hard opaque edge. Doesn't matter what basis you do, taking a Fourier transform of a hard edge is going to ring. So we need to investigate what the beam is doing. And just for reference, the beam level at the horizon is at roughly 0.3%. So in summary, we need to view these traditional radio astronomy techniques through the concept of the EOR. Discreteness of the experiment is a problem for calibration. And interactions at the horizon with the beam create an infinite UV response that hinders not only EOR, but potentially many types of precision spectral science. Thanks. I'll take questions.